Hi, my name is Heng, and I'm presenting to you my final year project called Animal Hunt. But before I proceed on, I would like to take a few seconds of your time to do this activity we called Who Am I? I'll be playing a short clip of an animal sound, and all you need to do is just guess who is it. The hint for this is it's a bird. I hope you're able to guess who is it. If you're unable to, fret not, as I'll be telling you who is it on the next coming slide. So what you just heard is a bird called Asian quail. In Singapore, it is labeled as the infamous money bird, as we often hear it when we go to school or work. So yeah, you're wondering why I asked you to do this activity with me. Let me explain. What you've just done is what we call manual acoustic species identification, MASI. So MASI is the process of identifying animal species by the call, sounds, and vocalization. It is often used to monitor and study wildlife population, as well as assessing the impact of human activities. So how does MASI work? It starts off with an expert having to manually listen and analyze the audio recordings of an animal sound. So after they identify which animal is it, they'll annotate it. For example, out of a 1 hour clip, 0 to 4 seconds is the sound of an Asian koala. So after annotation, they have to cross-reference their result with known reference recordings to ensure the correctness of their result. As a result, MASI can be really labor-intensive and requires significant expertise. So my presentation objective for today is actually showcase a new software identification system that can recognize animal species automatically. However, this software is only able to identify Singapore bird species due to the scarcity of wildlife audio datasets in Singapore. So here's my content page, and hopefully by the end of it, you'll understand what is Animal Hunt and how it works. So let's talk about related works. It is important for us to analyze them, and it allows us to find a market gap and prevent redundancy. So here are some applications in the market shown in the table, and I've highlighted offline recognition and recognition of Singapore wildlife. As first of all, offline recognition is a characteristic that I believe should be implemented in the application, as imagine you're in a wilderness with poor or no signal, and the application relies on the internet to work. This scenario pretty much make your application non-viable. Secondly, the application market actually only caters to birds only, as well as bird species available in the North America and Europe region. As a result, there is no way for a Singaporean like myself to identify any of its wildlife in Singapore. And that's how Animal Hunt came to be. So what is Animal Hunt? So Animal Hunt is a mobile application specifically designed for real-time animal sound identification in Singapore. It utilizes deep neural networks to actually analyze animal sounds and classify them, and it serves as a tool for recording, analyzing, and learning about animals in a local environment. So let's talk about the system design for Animal Hunt. So here's the system overview of Animal Hunt. It begins with collecting and extracting datasets of animals and audio clips features during step 1, and the extracted data is then used to train a custom TensorFlow model that includes neural net model as a no-call detector under step 2, and this model is then converted into TensorFlow-like model that can be deployed into the mobile phone under step 3, 4, 5. So during deployment, which is step 6, audio is loaded in real time and is sent to a TensorFlow-like custom model which compromises your YAML and custom classifier. The application then calculates the species probability and identification quantity, obtaining the highest average among all the species it has detected. And based on this, the application will then give the user the final result. So now let's talk about system implementation and how was Animal Hunt implemented. Of course, you need to start off with data collection, data quality, quantity, and preparation. So for under bioinformation, we have collaborated with Singapore Birds Project as they have historical records from 2016, making their data really reliable. And for audio datasets, we are sourcing from Zenocanto, a website dedicated to sharing wildlife sounds from all over the world. And for datasets quality, we'll be using Zenocanto's quality rating system, as most of their audio datasets are sourced from the website. So here are the general recommendations. And for this project, we've been primarily using grade A and B as our training datasets and grade A to D as our testing datasets. And for datasets quantity, each burst in this project has a minimum size of 90 audio files and a maximum size of 150 audio files. And this is due to the scarcity of audio datasets for Singapore wildlife and also to prevent an imbalanced dataset in our machine model. And under audio dataset preparation, all audios are resampled to 16 kHz, and 16 kHz result in a smaller audio files and require less computation resources during training inference. And also, under bandwidth, many of the environmental and audio events is typically below 8 kHz. So using a higher sampling rate will result in redundant information. And for human auditory perception, our system is generally sensitive to frequencies up to 20 kHz, with most of the important information for sound perception occurring below 8 kHz. So using 16 kHz sampling rate captures sufficient information for audio classification tasks And for data availability, the majority of audio datasets are typically recorded in 16 kHz, so using the same sampling rate during training and inference ensure consistency and compatibility. So we have talked about animal datasets. What about environmental sound classification datasets? As animal audio datasets are not perfect and they contain noises from sources like passing cars or people talking, how do you prevent the model from classifying these noises as animals without using any environmental audio datasets? The solution is we will employ the concept of transfer learning by utilizing YAMNet. So let's talk about transfer learning first. So what is transfer learning? Transfer learning is a process of using a domain of a previously trained machine model and implement it into the new model instead of training everything from scratch. And this is only applicable when two models are intended to perform similar tasks. So why do we use it? Because traditional machine model learning is isolated and single task learning oriented. Knowledge are not retained and curated, and learning is performed without consideration for knowledge learned from other tasks. Whereas for transfer learning, learning new tasks relies on the previous learned task. And as a result, the learning process can be actually faster and accurate, and most cases need less training data. So what is YAMNet? YAMNet is yet another mobile network. It's a pre-trained deep neural audio network classification model trained on Google audio datasets to classify 521 environmental audio events, and is based on mobile net view architecture that was separable convolutional neural network, which is more lightweight than traditional CNN, making it more suited for use on mobile devices or devices with limited computational resources. So here are some classification events under YAMNet. So let's talk about network training, how we train the model. So first of all, we will feed the audio datasets into the model, and the audio will then split into frames based on frame steps and length values, where frame steps refer to the time interval between consecutive frames of audio samples, and frame length refers to the duration of each frames. The frames are then converted into small spectrograms for feature extraction and embedding, utilizing the mobile net view architecture. And then the extracted features in the form of embedding will be used for classification. So here's an overview of what I just said in pictorial form. So result. So these are results after we have created a model. And there's a reason why they are such a low training and validation accuracy, as the model it has been pre-trained on a large audio dataset that encompasses a broad range of audio categories. The model leverages transfer learning, so it involves fine-tuning the pre-trained model on a smaller audio datasets. And fine-tuning actually requires the model to adjust its weights and bias to improve its performance in the new audio categories, and as a result, this leads to a lower training and validation accuracy. So application features. So Heng actually supports multiple detection modes. So when we use single and multi, user can actually initiate identification process by pressing the red play button, which activates the spinner that indicates that it is processing the audio input from the microphone. So after they press the red stop button, the spinner will then be replaced with the identified animal. Whereas in live mode, the app will just continuously process audio input from the microphone and display the identified animal in real time. For collection phase, Heng actually supports filter and searching. And for the bioinformation page, Heng it serves as the do you know kind of concept where it provides you interesting facts about the animal, such as scientific name, residential conservation status. So now it comes to the conclusion of Heng. Heng is an innovative tool that uses deep neural network to monitor animal activity locally. And it provides a unique approach to animal activity monitoring for wildlife observation, as you pretty much just use a phone and its microphone to discover an animal through the sound they make. As a result, this serves as a starting point for users to record animals and learn about animals in their environment. And lastly, encourages public participation in the data acquisition process. As if you want to know more about other animals, we need you as the user itself to give us data about them. So this is the end of my presentation. Thank you for your kind attention.